Okay, we're gonna talk about eigenvalues and eigenvectors and what they mean, what they do. But before that, let's do some plotting of some different things. So we have a matrix, right? We have this matrix M. This is 2, 3, 0, 4. And now I'm just gonna put some coordinates in here. So let's choose, for example, 2, 1. Okay. So we have that point 2, 1, A. So that's over there. Okay. And then I'm gonna apply the matrix M onto the point. So I'm gonna apply the matrix M onto the point A. And I'm gonna get the point 7, 4, because all a matrix really is a transformation, right? You give it some, you have a matrix, you give it some numbers to like multiply, and then it gives you an answer. So this is what you're doing with A. You're applying the matrix M to A. So you're doing 2, 3, 0, 4 times 2, 1, and you end up getting 7, 4. So that's what you get. Now let's draw a line between A and the point that you get. So it's A with an apostrophe after you multiply with the matrix. So you end up getting this line. Now I want you to notice that you have this negative 0.2, which is the y-intercept right here. So you can see it doesn't go through the origin, it goes through that point right there. Okay, let's choose another point, right? Let's choose, for example, negative 2, negative 3, for example. That's the point B. Let's apply the matrix once again. We're going to apply M to B. And we end up getting negative 13 and negative 12. And I want to draw a line between B and B with an apostrophe. And I end up getting this line right here. But again, look, this line goes through this point right here in the y-intercept. Okay, so now I want to get to some number, which if I apply this matrix to, the line is going to go through the origin. Now, how do I get that? So I already know the numbers, and I'm just going to give you the numbers now, and then we're going to see how to get to those numbers. So let's say I gave you the numbers. Let's say I gave you 1, 0 as the point, right? I gave you 1 and 0. And then I said, okay, apply the matrix M onto the point 1, 0. What do you get? You get 2, 0. Okay. And I want to draw the line once again between C and the point C with an apostrophe. And look, this line does go to the origin, right? It does go to the point 0, 0. Okay, so that number works. 2, 0 works. Okay. I mean 1, 0 works. Okay. What else could work? Okay. I know that 3, 2 will also work. Now let's see if this works. So now I'm going to apply the matrix M onto this point, onto the object D. And I end up getting the point 12, 8. And I'm going to draw the line between D and the point that you get when you apply the matrix M to D. And look, you end up getting this line right here, which also goes to the origin. Look, this is the point D. And then the point D with D prime is over here, or D with an apostrophe is over here. And then the line that connects them goes to the origin. So with these 2 points, the line goes to the origin. And I'll tell you that any line, so now, let's say you have any numbers. So I gave you the numbers 1, 0. So I gave you 1, 0. And then I gave you 3, 2. Is that what I gave you? I think I gave you 3, 2. Yeah, I gave you 3, 2. So if you have any scalar multiple of these vectors right here, so if I gave you anything with 1, 0, so k 1, 0 just means any number multiplied by 1, 0, or any other number, let's say s multiplied by 3, 2, then I end up getting the line that goes through the origin. So this line will go to the origin. If you apply the matrix 2, 3, 0, 4 to any of these points, right, to any of these vectors right here, and then you draw the line between the point and then the resulting answer when you apply the matrix, the line will go to the origin. Now, how do we know there's going to be 1, 0 and 3, 2? Because these are very random, right? If it was 1, 0 and 0, 1, okay, that would make sense. But it's 1, 0 and 3, 2. So how do we get there? So now this is where eigenvalues and eigenvectors come into play. So usually this is written like this. It's written as A times V is equal to lambda times V. So now this lambda is actually the eigenvalue. And then the V vector here and here is going to be the eigenvector. So if this equation is true and the eigenvector is not equal to just 0, 0, then this works. And then A is obviously the matrix that you're working with. So in our case, A is going to be this thing right here. Now, how do we get there? So we do this. This is the interesting part about it. So imagine we have the identity matrix, right? So in our case, in our 2 by 2 case, our identity matrix is just going to be 1, 0, 0, 1. So I'm going to multiply this identity matrix by lambda. So I'm going to have lambda times the identity matrix. And that's just lambda, 0, 0, lambda. Okay, so far so good. Now what I want to find is the determinant of the matrix minus the identity matrix multiplied by lambda, and I want to set that equal to 0. So how do I do that? Well, I have the matrix A is 2, 3, 0, 4, and I'm going to subtract this right here. So I'm going to have 2 minus lambda as the first entry. I'm going to have 2 minus lambda here. And then I'm going to have 3 minus 0 is just 3, so I'm going to have the 3 there. Then I'm going to have 0 minus 0 is just going to be 0. And I'm going to have 4 minus lambda, it's going to be 4 minus lambda. So I have that. Now I need to find the determinant of this matrix right here. So how do I do that? Well, I just do this times this minus this times this. So I have 2 minus lambda times 4 minus lambda minus 3 times 0, which is just going to be 0, and I want that to be equal to 0. So this is going to go away, and I'm going to be left with 2 minus lambda times 4 minus lambda is equal to 0. That means lambda is equal to 2, or lambda is equal to 4. So now these are the eigenvalues for our matrix 2, 3, 0, 4. Now how do you find the eigenvector? So an eigenvector V is just going to be of the form x, y, right? That's just the way this is going to be some vector in that form. But then look, we already have the equation. We have the matrix A multiplied by the eigenvector is going to give you the eigenvalue multiplied by the eigenvector. So let's do 2 first. You're going to do each eigenvalue one at a time, because each eigenvalue will have its own different eigenvector. So if you have 2, right, so I have the matrix 2, 3, 0, 4, original matrix, multiplied by the eigenvector xy is equal to 2 times xy. Okay, now what do I do? So now I just have simultaneous equations to solve. So now I multiplied these out, so I have 2x plus 3y is equal to 2x. I have one equation right there. And then I have 0x plus 4y is equal to 2y. So I have 4y is equal to 2y. Well, from this right here, we can say that we conclude that y is equal to 0. That's the only solution to this equation here. Otherwise, this is not true. So y is equal to 0. When y is equal to 0, you have 2x is equal to 2x. That means you can let x anything you want it to be. So let x equal anything you want. But to keep it simple, obviously we're just going to choose 1, right? We can't choose 0, because if we choose 0, we end up getting 0 and 0. But we can't have 0 and 0. So we let x be anything, and usually we just choose 1. So I have 1 and 0. So our eigenvector is going to be 1, 0. And remember, 1, 0 was one of the points that worked, right? Look, our point C, 1, 0, that worked with having the line intersecting the origin. So that worked. So that's the eigenvector. Okay, that's the eigenvector for when lambda is equal to 2. Now, let's check if this is correct. So I should have 2, 3, 0, 4 times 1, 0. That should give me 2, and then that should give me 0. And that is indeed 2 times 1, 0. So that is equal to 2 times the eigenvector. So we're good. So this does work. Okay, now let's do it when lambda equals 4. So let's go down here. So when lambda is equal to 4, what do we have? We have the matrix A times lambda is equal to lambda times the eigenvector. So once again, the eigenvector is also going to be of the form xy, right? We just need to find what x and y are. So let's do this. So we have 2, 3, 0, 4. Oh, this should be A times the eigenvector. So A times the eigenvector is equal to lambda times the eigenvector. So 2, 3, 0, 4 times xy is equal to, well, lambda is 4 this time, so I have 4x and 4y. So once again, we have two simultaneous equations. We can solve them. So I have 2x plus 3y is equal to 4x. Or I have 4y is equal to 4y. So I have these two equations now. Well, from here we can conclude that y is just equal to y. And once again, to keep things simple, we just let y equal 1. So let y equal 1. And then from there, we have 2x plus 3y is equal to 4x. So now I'm going to rearrange this. I'm going to bring the 2x here. So I'm going to have 3y is equal to 2x. And the good thing about these is that you don't really need to solve these equations. So you can just leave it like this, or you can write it as x is equal to 3y over 2. So when y is equal to 1, our x is going to be equal to 3 over 2. Or if you don't want any fractions, we can let y equal 2. So if we let y equal 2, then our x is equal to 3 times 2 divided by 2, which is equal to 3. So that's going to be our other eigenvector. It's going to be 3, 2. Now let's see if this works. So that means 2, 3, 0, 4 times 3, 2. What does that give you? That gives you 6 plus 6 is 12. And then this gives you 4 times 2 is 8. And this, in fact, is 4 times 3, 2. And 4 is our eigenvalue. And 3, 2 is our eigenvector. So you can see this does work. And remember, 3, 2 was the other point. 3, 2 was the other point. That's the point D, right? That works. where if you applied the matrix M to D, you ended up getting some point over there, and then once you drew the line between those points, it went to the origin. So you can see the visual representation of what eigenvalues and eigenvectors do. These are very, very useful, very, very common, and maybe in the next video we'll talk about the characteristic polynomials and how eigenvalues and eigenvectors can help you diagonalize a matrix. So I hope this made sense. All you do is you find the determinant of A minus lambda I, and you do the same thing for 3x3 matrices as well, by the way, or higher order matrices, and then you end up getting lambda equals to 2 different values, or you could have the same one value that's repeated. And then you find the eigenvector by using this formula right here. A times the eigenvector is equal to the eigenvalue times the eigenvector. So I hope that made sense. If it did, please like, share, comment, subscribe, and let me know what else you want to see in future videos.